Okay, I think we're recording. I would hope so. Hello, my name is Brian. It's week 6, and we're going to be talking about loops today. I'm not the biggest fan of loops, in part because, as I'll motivate throughout of today, and as we'll discuss in week 7, there are better strategies for repeating yourself when it comes to coding. But I think that approaching loops is really important in order for us to get a foundation on why the other methods are stronger, and also to give us an intuition on how the other methods are going to work. So we're going to be talking about loops, for loops, and while loops, and hopefully giving you a sort of general solution, a general strategy on how they work. And this will be portable to other coding languages as well. So let's get started. Here's an example, I think, of bad repetition. If someone wouldn't know better, they might find that the means of variables in the Swiss data set by typing in a line of code for each column. And it might look something like this, where you assign to an object like mean1, the mean of the Swiss data, just the fertility column, right? And you do that for each of the 6 columns in the Swiss data set. Now, the question I have is, can you spot the problems? I think now would be a good time to pause and look at this piece of code and try to spot the problems. I tried to put a few in there. Now, how upset would you be noting that there's these mistakes in here, something like this extract is missing. There's 2 mean 5s. Over here it says man. I think there's 2 fertilities. So one of the columns is incorrect. But how upset would you be if the Swiss data set had 200 columns instead of 6? And you try to approach a problem like this in this manner? It would be trash. You'd hate it. It'd be so much work, and it would be so difficult to troubleshoot it and make sure that you had all of the right information. What I want to motivate with this example is an approach that I would call good repetition. So we'll be learning this general solution today, and a better but perhaps more specific one next week. And what we're doing here is specifying a vector that we will iterate over in order to get the mean of each of the columns in the Swiss fertility data. So it'll look something like this. We apply to the Swiss means object. We're going to set names. Now, set names allows us to name items in the first argument with items in the second argument. So set names to this vector, this numeric vector, that is equal to the number of columns in the Swiss data set. So it's going to have 6 elements, and they're going to be empty. And then we're going to assign to each of those 6 elements the column names of Swiss. So now we're going to have a vector with empty elements that are named each of the column names from the Swiss data set. And then we'll say for each iteration, so for each element in this vector, sequence along the Swiss data set. So we're going to go through each of the columns in the Swiss data set. And what we're going to do is assign to the element that we're iterating over the mean of the Swiss data set at that element. And what we'll get back in return is what we were trying to accomplish in the bad repetition example. For each of the columns in the Swiss data set, fertility, agriculture, examination, education, and so on, the mean value of each of those columns. Now we're going to get into how all of these little things are working today in this course. But I want to show you this motivating example so you can see how this is less typing. And if we wanted to troubleshoot this, it would actually be less work than if we wanted to troubleshoot something like this. And you might be saying to yourself, well, Brian, I don't know if that's so true. I mean, look at all this. There's all these curly cues and commas and several subset operators. But I want to return to this question then. What if this had 200 columns instead of 6? Okay. This code would still run. this would work in the exact same way. We wouldn't have to change anything about this code if the Swiss dataset suddenly had 194 more columns. Okay, let's talk about the guiding principles for today. Don't repeat yourself. In programming, we call this the dry idea. Computers are so much better than us, humans, as doing the same thing over and over again. So writing code to repeat tasks for us reduces the most common human coding mistakes, something like typos, misreading fertility twice, that kind of thing. It also substantially reduces the time and effort involved in processing large volumes of data. So I'll show you an example later of how quickly for loops can run, but also just the think about the difference between these two examples, writing this for 200 columns and writing this for 200 columns would substantially reduce our time and effort to write things that don't have to repeat themselves. And lastly, compact code is more readable and easier to troubleshoot. So like I said before, the curly cues and things are all over the place, and it might seem like it's this big lift to troubleshoot these, but I would say take courage, it's going to be okay. We'll discuss how it works. And I would also note that things like writing for loops and writing my own functions, for me as a coder, I probably didn't get into doing that for my first few years of writing in R. And it was something that I would, every once in a while, you'd have to drag me along to make me do it. And it was okay. It's okay to learn this way. And it's okay to revisit things like these slides whenever you need to remind yourself how these things work. So it'll be all right. The agenda for today, we're talking about like programming TM, nerdy coding practices. For today, we're going to be talking about for loops and while loops. These are very general methods. They apply to many coding languages, if not most of them. And then we're also going to talk about vectorization to avoid loops. Vectorization is my preferred strategy for not repeating myself, for following the dry idea. But I wanted to motivate that we should learn loops in order to understand why we want to go to vectorization and how we would write code that is based on vectorizing. And then next week, we're going to be talking about writing our own functions, which isn't as scary as it sounds, and looping methods that are based on those functions. So in order to engage with week 7, I think we have to have a week 6 first, unfortunately. The other thing I'd like to say is that for your homework 5, you don't have to use for loops. So if this seems just like wildly crazy, this is so much computer understanding, that's not my bag, it's going to be okay. At least for this next homework, and then I'll be back in town and we can talk on Slack about how we're going to write our own functions, that kind of thing for homework 6. So let's start with what is a loop. I'm going to be bad here and cite Wikipedia. A loop is a sequence of statements which is specified once, but which may be carried out several times in succession. The code inside the loop is obeyed a specific number of times, or once for each of a collection of items, or until some condition is met, or indefinitely. So today we're going to be talking about code that is obeyed a specific number of times, or for each of a collection of items, or until some condition is met. We're going to start with for loops. I think these are going to be the most common loop that you'll run into as an R programmer in the social sciences. For loops are probably the most general kind of loop. They're found in pretty much every programming language. The logic of them is, for each of these values, in order, do this. Okay. So I'm going to explain in words what happens inside of a loop. For a given a set of values, first, you set an index variable, often called I, but you can call it other things, equal to the first value in your set. Second, you do some set of things, some calculations, depending on that current value. And third, you ask yourself, is there a next value? If the answer is yes, you update to the next value in your set, and then go back to the second item on this list and say, do some set of things based on that current value, and then return to 3 and ask, is there a next value? If the answer is no, you exit the loop. So we're going to be looping through values and repeating some actions, okay? And one thing to note, while I was preparing this lecture, I discovered that assembler, the coding language, had for loops as early as 70 years ago. 70 years. It's wild. Okay. So I'm not a big fan of learning from this sort of wordy description. I'm very much happy to see a picture. So here's a picture of what I was just saying, and I'll describe it here. So set object I to the first value, and then run code using I, our first value. And then ask yourself, are there more values for I? If the answer is yes, we set I to the next value, then run code using I, and then ask, are there more I values? And if the answer is no, leave the loop. Okay, so let's return to our Swiss example. So we set I to, let's say, the fertility column. We get the mean of the fertility column. We ask if there are any more columns in the Swiss data set. The answer is yes. We set I to the education column. We get the mean of the education column. We ask if there are any more values, and so on for all 6 columns in our data set. And until there are no more yeses to this question, we exit the loop. Let's look at an example using our R language. I'm going to take a sip of water. Sorry, I'm not on the cam. But I don't know if y'all have recorded lectures before, but I had to re-record this a whole bunch of times for little things, lawnmowers turning on out front, all that kind of stuff. Wasn't sure if I was even recording, you know how it goes. Anyways, so here's an example of a for loop. It says for I, so this will be our object that is going to represent our values within the loop for I in 1 to 10, so a vector of the numbers 1 to 10, print I squared. Okay. So what will happen is we'll get, when we run this code, we'll get output in our console that looks like this. It'll run 10 separate print commands, so they're all going to be on their own separate lines. But let's verbalize what happened here. So the first thing that happened was I got set to the first value in this vector. So I was the number 1. So I got set to number 1, and then it printed I squared. And 1 squared is 1, so we got this. But since there are more values in this vector, I got turned to number 2. It got assigned 2, and then we printed I squared, which is 4. And it did this for all of the numbers from 1 to 10. To bring a little bit more clarity to this example, here's this same piece of code, but just for a vector of the numbers 1 to 3. This is equivalent to running these 6 lines of code, having the object I, assigning it the number 1, and printing I squared. And then overriding I by assigning it the number 2 and printing I squared to get 4. And then overriding I by assigning it the number 3 and printing I squared to get number 9. Okay. So some conventions that I'd like to make you aware of as we move forward. We call what happens in the loop for a particular value one iteration. Iterating over indices 1 to some number n as an integer is very common. N might be the length of a vector. It might be the number of rows or the number of columns in a matrix or data frame, or the length of a list. But iterating over 1 to n, very common way that you might see for loops written. It's common it's a common notation for I to be the object that holds the current value inside the loop. If loops are nested, you will often see J and K used for the inner loops. This notation is similar to indexing in mathematical expressions, like the sum here. I will be set to 1, and we'll sum all of the numbers up until we reach n, right? This is describing a loop. Note that I and J and K are just normal objects. In fact, these are the same kind of expression. Where I is assigned here, this happens inside of a for loop. Okay, so I is just a regular object here, just like I is an object here. Okay. You can use any other names that you want other than I and J and K, even though they are the common iteration conventions. An example would be when iterating over rows or columns, I often use row and or column. Like I've said before, I often work with a lot of data that compares state level social inequalities. And so my for loops might have the word state or county to represent the iteration that I'm going over for some calculations. You can also iterate over characters instead of just integers and numbers. What we iterate over doesn't have to be numbers, 1 to n, or numbers at all. You can also iterate over a character vector. Here's an example. So we're going to assign to the sum letters object our letters vector, all the lowercase letters in the English alphabet. And we're going to subset to just the letters D, E, and F, and then say for I in some letters, print I. And it will return to us D, E, and F. And note that after you run this actually a whole set of code here, I will still exist in your environment as an object, and it will just take whatever the last value of your for loop was, because it is assigned to it, just like it was assigned in that example earlier. So I now just has the character string F in it. This is useful to us because it tells us, for me, I typically use this as a spot check to see that my for loop ran, right? If I'm iterating over states, and I'm excited to know that, oh goodness, what's the last state in the alphabet? Vermont, maybe? Oh, goodness. This would be a time where it's like really nice to not just be recording, and I could just have someone in the class like nod their head when I said something goofy like that. You know what I'm saying. The sequence along function, let's move on. The sequence along function creates an integer vector equal to 1 to the length of some object. So when you want to loop over something that isn't numeric, but you want to use a numeric index of where you are in the loop, sequence along is useful. Okay, so you want to loop over something that isn't numeric, but you want to use a numeric index of where you are in the loop. So sequence along is useful for this particular case. So let's say for A, in the sequence along some letters, print the pasting together of the string letter, our index here, A, colon, space, some letters, so our some letters vector, subset to our current iteration. And what it will return to us is letter 1, D, letter 2, E, and letter 3, F. So 2 important things to note here. A was used both for its numeric representation. Since we're using sequence along, this is going to give us a numeric vector, but also as a tell for what element of the vector we are going to subset in a different part of the loop. So you can get creative about what you would like your iteration object to do inside of a loop, and it can take on multiple tasks like this. Also note that the object A now contains the number of the last iteration because we use sequence along rather than in the last example where I was the letter F. So let's talk pre-allocation. Usually in a for loop, you aren't just printing output like we have in these examples, but you want to store some calculations, some results in each iteration somewhere. For instance, like when we were looking at the mean of all of the columns in the Swiss data. To do that, figure out what you want to store. That's the first step. You want to figure out what you're trying to store at the end, and then pre-allocate an object of the right size as a placeholder, typically with missing values as that placeholder. For instance, we had those 6 columns in the Swiss data set. We can pre-allocate a vector that has 6 elements, all set to NA. This would be a use case for this. Some examples of what you might want to pre-allocate based on what you are trying to store. Let's say you have a single numeric value per iteration. You can use the numeric function, and then whatever your number of iterations that you're trying to do here is. Let's say you want a single character value per iteration. You can use the character function and however many character values you want to store. Let's say that you are going to store some sort of logical vector. You can use the logical function and however many iterations you want to store. Let's say you want a numeric vector, so not just one value, a whole vector per iteration. You can use the matrix function and say your data is equal to NA, like we did in homework 4. Yeah, like we did in homework 4. And then set the number of rows equal to the number of iterations you'd like to do, and the number of columns equal to the length of the vector. You can have some complicated object per iteration by using the vector function, and you can specify that you want a list. And so this will actually return to you a list based on the number of iterations here. I always thought this was kind of a convoluted syntax. I used the vector function to create an empty list. This is only in the case that you want to pre-allocate. So we'll get into why this convoluted syntax might not be what you're going to use in the future, but we'll get there. So let's look at some examples of pre-allocation. So here would be numeric pre-allocation. We have some sort of data that we want to store that is numeric. So we can make an object equal to the number of iterations that we'd like to store. So we have 10 iterations we'd like to do. We're going to assign it to the object called iters. And then we're going to have an object we're calling output. We're going to assign to it the numeric function with iters as the number of iterations it's going to take on. So this will be, let me pull up R so you can see. this at work. Okay, so we assign here iters. Note that my environment's down here. I'm at my home computer, so my environment's over here instead of right here, like you are probably used to. But now our output object has 10 elements and they're all 0, which is the same as saying it's a numeric vector that's empty. And then we're going to run this code, and it's going to populate our empty vector with stored materials based on our for loop, and we can display that output. So let's return to the slides. Okay. I'm going to check that that's still sharing my screen. Okay, cool. So now for I in 1, 2 iters, assign to the output at the element of our iterative value of I, assign to it I minus 1 squared plus I minus 2 squared. And so this will now store all of the calculations per iteration in our output vector that we've pre-allocated for each of the elements in the vector. So for 1, when I is equal to 1, or when I is assigned 1, the first element of this will get assigned 1 minus 1 squared plus 1 minus 2 squared, and we'll get 1. And then we have more values, so we'll assign I the number 2. This will assign to, that means within the loop, we'll assign to output at the second element, 2 minus 1 squared plus 1, or 2 minus 2 squared, which is also 1. And then we have more values, so we'll have 3 at output, and the third element will assign to it 3 minus 1 squared plus 3 minus 2 squared, which is 5, and so on and so on. So a few things to note here. So the steps where we set a number of iterations, 10. We pre-allocated a numeric vector of that length. So we have this new output vector. We use the numeric function to pre-allocate 10 spots, or the amount of iters spots in that, or elements within that vector. And then we ran iterations where the output is a mathematical function for each iteration number. And one thing to note is that we could have skipped this step, but it's useful if you want to make this code flexible. So if we just put 10 right in here, it might not be obvious to another user who is going to use your code how this is working. Whereas if you put 10 up here, it can be pretty quick to say like, okay, we'll just change this number and it'll all go. But now we can use that output. So we had that output, and we can now display on the x-axis the number of iterations, and on the y-axis the output that was in our vector. Okay, the set names function, which I used in the first example of what I called good repetition. The function set names can be handy for pre-allocating a named vector instead of pre-allocating a numeric vector. So in this example, we assign to an object called names to use. We're going to paste to 0, or paste 0, which means to combine a string without any spaces in it, iter, and the first 5 letters of the lowercase English alphabet. And what we'll get is a vector with the elements iter A, iter B, iter C, iter D, and iter E. Without set names, you would have to do this like this. You would have to say, we're going to make a vector and assign it an empty vector with 5 elements, and then assign to the names of a vector the names to use. So these names to use. Set names allows us to condense this into one line. Something like a vector assigned to it set names, the vector that we're making, a numeric vector with 5 elements, and then the names to use is going to be the names that are set to that vector. Let's get in some water. Okay. Now let's look at an extended regression example. I know that this class doesn't assume that you know any statistics, but I think that this example helps motivate what kinds of elaborate structures we can build with for loops, and perhaps build some more intuition about how and why we would use them, rather than just making some plots of some math, okay? So suppose we have some data that we want to try fitting several regression models to, okay? We want to store the results of fitting each regression as elements of a list so that we can compare all of the different models. To do this consistently, we'll write a loop. That way, no matter if we had 2 models or 200 models, we could use the same code. After we do this, we'll try something more advanced with loops. That's called cross-validating regressions to get an estimate of their true accuracy and predicting values out of sample. So here is where I think we're getting pretty dicey on how much statistics training we all have. And that's why I'm a little bit bummed I'm not going to be able to sit there and witness folks just like check out of watching this lecture, but that's okay. So we're going to start with simulating data. Let's simulate some fake data using the rnorm function to generate random values from a normal distribution. We're going to set C to 755 so that if you wanted to run this code, the values would always be the same. We're going to generate a data set with 300 observations. So we're going to create this object here, N for 300. Then we're going to make, assign to X, 300 draws from the normal distribution with mean 5 and standard deviation 4. And then we're going to assign to the simulated data. We're going to make a data frame where our X column is going to be equal to X, which are our draws here from the random normal distribution. And our Y is going to be equal to some carefully massaged mathematical equation in order to make sure that Y is dependent on X with some uncorrelated, normally distributed residuals. If I'm saying a lot of words that don't make sense, it's okay. Suffice to say, I'm making some data that's simulated where we have some X value that we're interested in evaluating and some Y value that's dependent on that X value. Also, if you followed the 2014 scandal in political science, a grad student faked data for a publication in Science, you know, the big journal Science. And it is believed that he used the rnorm function in order to add noise, just like I've added noise here, to an existing data set to get his values. That's a shame. Reading this story makes me sad. The economy of publications and all that. Let's move on. You know what Lord Byron says, if I laugh at any mortal thing, 'tis that I may not weep. So let's move on. So we're going to plot the simulated data, and here's what it looks like. We made a ggplot here with X on the x-axis and Y on the y-axis. It's just a scatter plot, and we can see that our X and Y do have a relationship of some kind. Perhaps it is a curvilinear relationship, and we can fit multiple models in order to test that hypothesis. So let's talk about our candidate regression models in our example here. Let's say we want to consider several different regression models to draw trend lines through the data. We have the intercept only model, we'll draw a horizontal line that best fits the y values. So that's the same as saying that the expected value of y is just equal to the beta is at 0. We have a linear model where we will draw a straight line that best fits the y values as a function of x. So now we're saying that at the slope, we're going to draw a line that probably has, or at the y-intercept, we'll draw a line that has some slope that's based on the x values in our data. We're going to fit a quadratic curve. We're going to draw a quadratic curve that best summarizes the y values as a function of x. So rather than just saying that x has some sort of straight line relationship between the data, we actually think that it has a parabolic shape. And we're also going to compare a cubic model. We're going to draw a cubic curve, so one that has 2 bumps in it instead of just one, like a quadratic model, as a function of x. And we don't need additional covariates. We can just square our x here and cube our x here in order to draw these kinds of lines in our data. So we're going to pre-allocate a list. Let's make a named character for the formulas we'll use in the linear regression function lm. So we're going to assign to our models object our intercept only model, which is going to be y, is given to us by 1, which is just to say, this is the shorthand for saying that y is equal to just the intercept of wherever the line points to, typically the mean of the data. We have a linear model where y is a straight line through x, or x draws a straight line through y. The quadratic model, which we can square our x here within the model using this I nomenclature. We don't really need to get into why we would do this. And the same thing, we just want to add our cubed version of x in order to get that second curve if we'd like in our regression lines. Then we'll pre-allocate a list to store the fitted models. So we're going to assign to this object fitted LMs, a vector function, right, to make a list. Again, it's this very convoluted syntax in order to make an empty list that's equal to the length of our models object here. And then we're going to give to the names of the fitted LMs the names of the models vector that we've made up here, so that each of the elements of this list will have the same names as the elements of the models vector we're going to be using. And now when we look at it, we'll see we have an empty list with an intercept only element, a linear element, quadratic, and cubic element. Okay. Next, we're going to fit the models for our for loop. We'll loop over the models vector, which specified how the formulas are going to go into our regressions and also what their names were. We're going to fit each one, and we're going to store it in the appropriate slot in our pre-allocated list that has the same names of the models that we're going to fit. Okay, so here's what the for loop is going to look like for that. Within the for loop, we'll see that the formula function will convert the character string describing the model to a formula object that's readable by LM. So over here, this is how R receives formula objects. This is what the syntax looks like as a character string. But if we want LM in particular to be able to read a character string and convert it to a formula, we use the formula function. Okay, so let's talk about this for loop. What it does is it says for each model name, which we refer to as mod, right? Doesn't have to be I, we can call it mod. For each model name, fit a linear regression using the formula with that name. Okay. And then assign the output to the element of the list with a matching name. Okay. So for each model, in the names of the model, so names models here, we'll just return back each of the names that we specified before from our models vector. So for each name in our models vector, assign to that element with the same name in our list, our empty list with the same names, assign to it the output of the linear regression, drawing from the formula in the models vector at each particular model, and always using the simulated data. So we're always using the same data. Okay. And then we're going to get predictions. To plot the fitted models, we can first get the predicted Y values from each at the X values in our data. So we're going to assign to our predicted data our sim data. Okay, and this allows us to predict what our Y values would be given our X values and our model. If that doesn't make a lot of sense quite yet, that's okay. This will get there. But what's going on here is for each named regression model output that we made in the last for loop, first, get the predicted values associated with that model using the predict function. Second, save each of those predicted values as a new column in our predicted data set. And the values of mod will be the new column names. So all of those things are going on in this for loop. So we're making a new column in our predicted data. So recall that our sim data just has our X values and our Y values. We have now copied it to the predicted data. And now we assign to the predicted data an element that we're calling mod. And since those don't already exist in our predicted data, at this stage, it is going to create a new column based on the predictions from our particular models with the same name using our data. And so here's what the predictions will look like. It'll say we have some X value 3.646. Our associated Y value in the original simulated data is negative 0.174. And in the intercept only model, it predicts that this value of X corresponds with a Y value of negative 0.428 based on the intercept only model. But since the intercept only model only guesses the average, we're going to get the same value for all of these things. It doesn't take into account the X values, right? In the linear model, it assumes a straight line. So at the 3.646 value here, we can predict that our Y value will be negative 0.399. In our quadratic model, we can predict it'll be negative 1.199. In our cubic, a negative 1.189. Okay, I know this is looking at a lot of data. We're going to graph it here in a minute. So we want to gather our predictions, gather what pivot longer used to be called. We can use tidier's pivot longer function to tidy these predictions, then set the levels of the model variable. So we're going to take the tidier, or we're going to use tidier. We're going to make tidy predicted data by assigning to it the predicted data, and then pivot longer from the third column over. So after X and Y, from the third column over to the length of the predicted data. We're going to take the names and we're going to call them model, and the values we're going to call them predictions. And then we're going to mutate the models are going to be equal to the factor of models, and the levels are going to be equal to the names that we've already provided. Okay, so now that we have levels equals names sets the model levels to be in the same order as our original vector, rather than having them be out of order. So this is just like a thing to make them look nice. And if we look at the first 6 rows of this, we'll now see that we have some X value, some Y value, and then the intercept only model and the prediction. And we have that it'll duplicate these things, but since they're over different models, it's okay. And this allows us to draw graphs that look nice in ggplot, right? So we'll use ggplot2. to plot these tidied up predictions, you'll see us use multiple data sets on the same plot. For instance, look at the geom line calls. This is something I didn't demonstrate in ggplot2's week because I thought it would be like kind of a lot to think about. But I think that we have a little bit more skills under the belt. We can see how this works. So we'll take the ggplot2 or ggplot, initialize that, and then we'll add a geom point. That's just our simulated data, where the aesthetics are x is equal to our x values and y is equal to our y values. So this will give us that same scatter plot that we saw before, right? And now we're going to add a geom line based on our tidy predicted data, where we have our x values defining where on the graphical space is going to be on the x-axis. And our y values are going to be equal to the prediction from the model rather than the y values that we observed. And we're going to group by the particular model, either intercept only or linear, or quadratic, or cubic, as well as color them by that. And then add a little bit of transparency and make the lines a little bit bigger. And let's see what we got. So now we have these plotted predictions. These are the predicted trends from our regression lines. Our intercept only model here is going to be a straight horizontal line. Our linear model assumes some negative slope, but it doesn't seem to capture very many observations, right? Like this green line doesn't seem to fit our data all that well. Whereas our quadratic line is able to capture the curve of our data as well as the cubic line. They're almost identical. In fact, it's very difficult to tell that the purple and blue are overlapping like that. So which one looks best to you? I think it's pretty clear that the quadratic and cubic are both pretty good. But one question we might have is which one's better? So now I'm going to get into a complicated example of a for loop, but one that's not too complicated, I think. So we're going to use a cross-validation method. What is it? Cross-validation is a widely used method to estimate how well a model makes predictions on unseen data. That is data that was not used in fitting the model. So the procedure is you'll split your data into a k number of folds or pieces. And then for each fold from 1 to k, fit the model to all the data except that fold. And then you're going to make predictions for the omitted data in that fold. And then using that information, you can calculate the mean squared error or your favorite measure of accuracy comparing predictions to actuals. I'm going to use the mean squared error today. The mean squared error defined like this. And a model that fits well will have a low mean squared error. Models that are either too simple or too complicated will tend to make bad predictions using this measure of accuracy. And thus, they'll have a high mean squared error. So here is an example of how this is going to work. We have our real y and x data. And then we're going to take this folded row and we're going to set it aside. And then we're going to have the other, not part of the k fold set of data, fit a model. And we're going to use that model to predict the data that we've set aside. And this will become our predictions for our first k fold. Okay. And we'll keep doing this. Then we'll do it for the second row. And we'll use the first, third, fourth, and fifth folds in order to fit a model to predict the second row, and so on for each of our k folds. And we'll get all the way through each of our k folds until we are finished predicting all of our data set. And that is how k-folds cross-validation works in a nutshell. So we're going to pre-allocate here for our cross-validation technique. Let's split the data into k equals 10 folds. We'll make a new data frame to hold the data and sampled fold numbers that we will add to the prediction later. So we'll get the folds using the sample function without replacement on a vector, as long as our data that contains, as long as our data that contains the numbers 1 through k repeated. Okay, so we're going to assign to k 10 because we want to have 10 folds. We're going to assign to our cross validations predictions our simulated data, very similar to how we made that predictions data earlier. And then we're going to assign to the fold column in this data. And we're going to sample, and we're going to repeat for 1 to k, length that out, the number of rows in our cross-validation predictions, and we're going to replace equals false. So what this is doing is saying sample a number 1 through 10 that's equal to the number of rows in our data set, and don't replace anything. So this will assign to each row a number that will identify what fold it is. Okay. And then we're going to add to our cross-validation predictions an NA for each of our columns that are associated with our named models. But those don't already exist in our cross-validation predictions data frame. So one way we might do that is by using the subset operator for all of our rows, and the names of our models, so that vector that we use to fit our models, we're going to assign NA, and we'll add for each of the names in our models a new column that only has the contents NA. Okay, so here's how our CV predictions data is looking. We have our original data. We have assigned to each row a fold that is going to fairly sample and give out identifiers for each of our 10 rows, or each of our 10 folds. And then for each of our models that we fit, we have a pre-allocated column that is empty. It's just full of NAs. Okay, so next, let's loop over each model. We're going to assign to the models the mod object in order to iterate. And then within each model, loop over each fold k to fit the model and then make predictions. So for each model, we're going to do the k folds cross-validation technique. Our data is going to look like, or our for loop for that is going to look like this. For mod and names models, so for each model, and then within each model, we're going to say for k in 1 to the number of k folds that we're interested in. So recall we made the capital K folds object earlier for 10 folds. And what happens inside of that for loop is we're going to assign to the fold rows the CV predictions data, and then only keep the fold rows that are equal to the current k. Okay, and we're going to set that data aside, and then we're going to fit a model to the data that's not in the fold. So we're going to make a temporary model and fit the data using our same formula for each of our models. And now our data is going to equal to our CV predictions that are not our fold rows. And then we're going to predict our fold rows. So we're going to make a CV predictions at our fold rows for each current model, assign to it the prediction of our temporary model, which was all of the data that was not in our current fold rows. And then the new data that we're going to assign to predict is going to be our current fold rows. Note, the models are fit without the fold rows, but prediction is done on only the left out fold rows. Again, I know this is a part where I tend to lose a lot of people. So it's kind of a bummer that I'm recording this. That's okay. So let's see which model did best after we've run this for loop. So let's write another loop to compute the mean squared error of these CV predictions. The squared error is equal to the difference between the real values and the predictions squared. The mean squared error is the mean of all squared errors of each of those predictions. Okay, so we're going to pre-allocate to CV mean squared error. We're going to set names for a numeric vector that's equal to the length of the amount of models we have, and it's going to have the names of those models. And then for each model in our set of models, assign a predicted squared error, which is going to be our predictions, our y values of in our predictions data, minus the predictions at that particular model squared. And then we're going to assign to our pre-allocated CVMSE for each model the mean of the predicted squared error. And now we can tell that our quadratic model fits just so slightly better than the cubic model, because we want our cross-validation numbers to be smaller in order to be more accurate. But in fact, I would actually choose the quadratic model anyway, back when we were looking at the graph here. And the reason is that you typically want a less complicated model in general, if you can. So it's typically the case that no matter how many squared terms, cube terms, and terms that you add, it will improve model fit. So we probably want to take the one that has the lowest amount and still fits the data pretty well. So we didn't have to go through all this to analyze that since we already did the drawings, but I did want to show you how the power of loops through a more complicated example. I'm sure I'll be getting questions on the Slack about it, and that is a-okay. It's also nice to have this in your pocket for when you take a class that's probably about, I don't know, maximum likelihood or something, and they ask you to fit a cross-validation, a k-fold cross-validation. So let's move on to talking about conditional flow. So we're going to be talking about the if function and then using the else trying to think about what the word is. If function, then else format for doing logical checks. You've seen if else, its own function if else, before for logical checks on a whole vector, for checking whether a single logical statement holds and then conditionally executing a set of actions. For checking whether a single logical statement holds and then conditionally executing a set of actions, we'll use the if function and else. For instance, we'll say for I in a vector of 1 to 10, if I, when it's divided by 2, is equal to 0, so this modulo operator that we've used in some pet examples before, is just division, but it will return back the remainder. If I divided by 2 equals 0, print the number I is even. Else, if I is divided by 3 and it equals 0, print the number I is divisible by 3. Else, print the number I is not divisible by 2 or 3. A word of warning, else needs to be on the same line as the closing bracket of a previous if. So you probably want to keep a very similar format as I have done here when doing an if else like this. One thing I want to note about if else is like, it's really great for conditionally executing a set of actions. So in other words, I'm saying when there is a special case, you can use an if else to handle that case within your for loop. And in fact, what you'll find when you look under the hood at some of the functions that we run, often what happens is they're using if else statements like this in order to capture some exceptions that occur. You'll see this a lot in ggplot if you ever want to look at the code of how your ggplot runs under the hood. So here's the output for our integers 1 to 10. The number 1, not divisible by 2 or 3. The number 2 is even. The number 3 is divisible by 3, and so on and so on and so on. So aside from this previous toy example, the if function statements are useful when you have to handle special cases. The if function statements can be used to make a loop ignore or potentially fix problematic cases. They're also useful for producing error messages by generating a message if an input value is not what is expected. So this is often what's going on. I mentioned the ggplot example. Perhaps you were making a ggplot and you ran into this common sort of mistake of doing something like this. ggplot, we're going to say yes, or data equals Swiss. Okay. I haven't loaded ggplot, but if you do this and then use type before like geom_line, ggplot will not say some inscrutable thing. It'll say you need to use a plus here instead. Actually, I think it's need help. I'm sorry, but I need to. Okay. And then yes, I was going to make an example of this data. This, and then if we pipe this to geom_line, couldn't find the function. My goodness, I just want to do a quick example. Can we just do that? So now the error will say, did you use a pipe instead of a plus? And the way that they make it say that is using an if else. So let's look at an example of using a loop to load data. One common use of a loop is for loading many individual data files at once, like an entire directory of Excel files, to combine them into one data set. So let's say we have a folder filled with .csv files. We can get the file names in the folder using the list.files function. So we can assign to our file list the list.files and our particular folder that has all of the data that we want to use. So one thing I also want to note is I tend to use this dot example or this dot syntax when I am specifying a folder that's nested in my current working directory. And this is for two reasons. One, it reminds me that inside of my current working directory, there is a folder called example data, and we're going to look inside of there in order to get our data. But one thing that we can also do using relative paths is add another dot before this one to go to the folder that our current working directory is nested in. So it actually allows you to go out into the larger folder that you're currently inside of. Those of you who've used like shell script before will know what I'm saying. Anyways, inside our example data folder, we have 10 CSVs that are example data sets. Okay. So let's populate an empty list of the same length as our file list, which has all of our 10 names of our data sets. So we're going to assign to data list. Again, we have to use this weird vector syntax in order to create an empty list. Vector and then we're going to specify list in quotes in order to create that list, comma, and then the length of our file list. And then for nice object names, we can use stringer to remove the .csv from that file list. So we can assign to our data names. We'll use the stringer package, which we will cover more in week 8, I believe. We'll use the string remove function from that package on our file list and remove the .csv. So now we'll just have these example .1s without the CSVs as our names, and assign to the names of our data list, this empty list we created before, our data names, which are just the names of the files without the .csv at the end. Then we'll run a loop that reads in each data file and writes it to the appropriate element of data list. So we'll use the reader package, and we'll say for I in sequence along our files list, recall that sequence along takes something that's a character vector and then creates like a numeric vector for each of the elements in that vector is applied to its argument. And then inside the loop, we'll assign to the data list at a particular element the data name that's specified by the data names at the element within the data names that we're going to use by the number of the I. I'm sorry, I'm really messing up the description here. I'm sorry if this is confusing. And then assign to it the read CSV function of our example data and our file list at that particular iteration. And when we look at the first element in our data list, we'll see that we have successfully brought in our example data for the first data list in our folder. So now we can look at the names of each of these elements. And this is a pretty good strategy just to make sure that we are capturing the things that we'd like. Names, ID, X, and Z, names, ID, X, and Z. In this case, every data frame has the same columns. So we can combine them all into one data frame very quickly and efficiently. So we can say, apply to the complete data object, or assign to the complete data object, bind rows are data list. And so bind rows will do as it sounds. It will bind the rows together of data frames and match them together for the columns that have the same names. And now when we look at the glimpse, rather than the structure of our data, we see that it has 10,000 rows, 1,000 for each of our data sets, and 3 columns are ID, X, and Z columns. Okay, now we're going to discuss while loops. A lesser used looping structure is the while loop. Rather than iterating over a predefined vector, the loop keeps going until some condition is no longer true. Okay, so let's see how many times we need to flip a coin to get 4 heads. So we're going to assign the number of heads to 0 to start, the number of flips to 0 to start, and then we'll say, well, the number of heads is less than 4. So right now, the number of heads is 0. Well, the number of heads is less than 4. Are going to assign to this coin flip object a draw from the random binomial distribution, which will allow us to do random draws from a coin flip. A binomial distribution is just a successive draws from coin flips. And then if our coin flip returns a 1, then assign to the number of heads plus 1, and then assign to the number of flips plus 1. Okay, and so what's going on here is it's saying while the number of heads is less than 0, do a coin flip. With the result of the coin flip, add to the number of heads or not, depending on the result, and add to the number of flips, and then run it again. And it'll keep doing this until the number of heads is 4. And for this particular seed, it takes 6 flips to get 4 heads. Yeah, I'm realizing now, I personally find it kind of difficult to implement while lists or while loops for a lot of the things that we're going to do, particularly because it's easier to vectorize while loops, in my opinion, as we'll discuss right now and next week. So we're going to talk about vectorization. So vectorization makes it a lot easier to repeat things than doing loops. And here I'll show you an example. So here's a non-vectorized example. We have a vector of numbers, and we want to add the number 1 to each element. So we're going to say my vector is going to be assigned 100 million draws from a random normal distribution. And we're going to use a for loop to add 1 to each element of the vector. So we're going to start the clock. This proc time allows us to calculate how quickly something runs in R. So we're going to, it basically tells you what time it is immediately when we assign this. And then later on, we will do it again in order to check how long something takes to run. So here we will assign a new vector. We're just going to repeat NAs equal to the length of my vector. And then for each position in our 100 million length vector, in 1 to the length of this 100 million length vector, assign to the new vector, which is just a bunch of NAs right now, at each position, my vector at that same position plus 1. Okay. And on this particular computer, it takes, I think 5.38 seconds in order to run a plus 1 here. Recognize that we can instead use R's vector addition, which recall we called recycling, vector recycling. I believe that was in week 1. So we're going to call it vec start in our proc time. And we're going to say new vector, assign to it my vector plus 1. And recall, since this is divisible by 100 million, or 100 million is divisible by this, we can just recycle this operation. And now it takes about 0.25 seconds, or yeah, in order for this to run, rather than the for loop. Okay, and if we divide those, we'll find that the vectorized method was 22 times as fast at calculating plus 1 to each of the elements of this 100 million length vector. This is an important thing to recognize because vector and matrix arithmetic is implemented using fast optimized functions that a for loop just absolutely cannot compete with. Just not even close. So typically, if we want to repeat ourselves and we want to save time, we will want to vectorize things. We want to take advantage of things that recycle rather than write for loops. So next week, we're going to do that. But this week, I wanted to help us get started with our particular for loops methods in order to get that foundation so that we can understand and recognize when it's prudent to do some sort of recycling and when we might have to just deal with writing a for loop. Some examples of vectorization that make things a lot easier are base functions. A lot of the vectorized things are base functions in R. And the rationale is that since they're built into the fabric of how R functions, they can make things run a lot faster. They're often under the hood written in very simple languages like C and C++ and all that allow to really maximize how fast a computer is doing something. But functions like row sums, call sums, row means, and column means give sums and averages over rows or columns of matrices and data frames. And they're a lot quicker than a lot of our other for loopy kinds of methods for doing these things. For instance, we can create this matrix. We'll call it a matrix. That is the numbers 1 through 12 with 3 rows and 4 columns. And now when we run row sums on this matrix, it'll calculate for us the sums across the rows very quickly. In this pet example, it's not clear how quick that happens, but when you have these really ginormous matrices that are built out of your really large data sets, this matters a lot. Some other vectorized examples that you might run into are computing cumulative properties or cumulative quantities. So like the cumulative sums, cumulative products, cumulative min, cumulative max. They'll give back a vector with cumulative or running totals, right? So the cumulative sum here, 1 to 7. You'll find that sometimes in dplyr, it can be pretty difficult to write things that are recursive. Things that will loop through a column and add based on the earlier values in the column. And vectorized functions like these make that way easier. Otherwise, you might end up having to write a loop yourself. Pmax and pmin can take a matrix or a set of vectors and output the minimum or maximum for each position after recycling. Okay, so look at this function, pmax. It'll tell you the position of the maximum at each position. So here, 0, 1, and 2 is 2. 2, 1, and 2 is 2. And 4, 1, and 2 is 4. Neat, right? Whereas writing a for loop that would read this and then make this can often be really, really tough. Vectorized file loading is also a lot faster than that for loop example that I showed you earlier. For instance, the Vroom package allows for vectorized loading of delimited files. For instance, here, the complete data Vroom object is going to get assigned Vroom. The Vroom function allows us to take our list of files in that same folder and keep the full names. And it will do all the work that all of those loops did and all that work did in one line. It already does the bind rows part of it, even it has 10,000 rows and 3 columns here. It'll do that part for you. Those kinds of things really save us a lot of time. And I'll show you next week yet more methods that will save us more time. For the homework for week 7, right? The homework that's due on week 7 is homework 5, part 2. It'll be due midnight Wednesday as per usual. Thanks.